the web. A bit about India and Pakistan, again motivated by the fact that Professor Nath was talking about this in our last lecture. So I have another little vignette. To be honest, you could blame this on age, but I can't remember if it was 1996 or 1997. One of those years, I was running experiments at Los Alamos. I was a brand new staff member at Livermore. I just finished my postdoc. And there was an email that went out saying that somebody from South Asia, the South Asian area, was very interested in Promethium-142. So raise your hand if you've gone to the National Nuclear Data Center website. Yeah. So you can imagine that when you click on these things, we in the US NDP, we keep track of who's clicking on what and where the IP calls are coming from. And actually, to be fair, this is nothing that Google doesn't do as well, right? And they know, but obviously somebody is watching this. Mostly at the US NDP, what we care about is like what fraction of our users are from the nuclear energy industry, what fraction are from academia, because we try to adjust our efforts so that we match up with that. This was clearly coming from South Asian region. And there was an extraordinary degree of interest in Promethium-142. And lab management wanted to know whether this was benign or not. And so I was just a couple of years out of graduate school, and I was just a nuclear physicist without really any sort of background in application specifically. My background was quite basic science oriented. But I went and I looked, and I found that there was something interesting about it. And I wrote a little couple of page email back to the person. The person who wrote this was the head of our physical data research program at Livermore. This is the program that's charged with getting the correct data, like materials properties, nuclear cross-sections, plasma physics properties, etc., to enable reliable calculation as part of stewardship science. It was our physical data research program, and his name is Bill Goldstein. And he's now the director of Livermore. But Bill's original background was this. He was the head of the PDRP program. Okay. So let me talk a bit about Promethium-142. Do you remember I showed these plots before? This is a plot of the fission yields. This is for neutrons on U-235 fission, okay? And this is where most of the feeding is coming in. And trust me when I say that this is on the neutron-rich side of stability. But if you don't trust me, I will do before, after. Before, you see the black, that's stable. And you can see that really this region is all to the right of stability, right? You see that, okay? And that's what you expect because uranium-236, the nucleus that's fissioning, has a much higher neutron to proton ratio than lighter nuclei. And that's, remember again, where that comes from, that as we start adding nucleons to the nucleus, you fill up the proton well first. It's shallower. And so you end up with more neutrons. Okay? And if I look in the same way at plutonium, that's what it looks like. Again, it's to the right of stability. Actually, it's very slightly less to the right because the neutron to proton ratio in Pu-239 is slightly lower than it is in U-235, or I should say Pu-240 or Pu-236. Okay. Now, remember, because these things are neutron-rich, when they're formed, when the nucleus fissions, they've got too many neutrons. What will it do to regain stability? Beta minus decay. It will turn some of those neutrons into protons. That process is slow. It takes a while. Okay? You can see it here. And I give you an example for, remember also that the fission fragment yields are this kind of two-peak distribution. Strontium-94 is kind of close to a peak there. You've got a peak close to 137, like xenon-140 is one of the peak elements. 14 seconds, you do beta decay. You've turned one of the neutrons in xenon into a proton, so now it's xenon-140, and then barium-140, and then you see it gets a lot longer. When you're rolling down a sharp cliff, right, when the curvature begins to become less sharp, you roll more slowly. okay? 13 days, 40 hours, finally down to stability, okay? And the same thing going on with strontium 94. So what this means is that if you have a fission event, a weapon, a reactor that was running over a long period of time, any place where you have fission, you don't usually see these short-lived things. You see what comes after the decay has occurred. Downhole, kind of the typical number that we were doing when we were doing underground testing, we liked nuclei that had sort of radioactive nuclei that had like a 3-day lifetime. Okay, it's really hard actually to get debris out of a downhole shot. You have to bring a drilling rig, the drill has to come in at an angle, it's quite complicated. You're basically aiming, you're trying to guesstimate where the molten glass slag pool is at the bottom of the cavity that you've opened up. It's very tricky to do these sorts of things. And it takes time. Sometimes you would drill that and miss, and you have to come back and go through again. Okay, so it takes time. And so what you usually see is something that was many beta decay steps removed from what was originally made. And then you have to try and back this information out. Now, we can do that with some degree of reliability, but not fantastically well. That's the truth. We need to know information about how much every one of these steps is fed. It's not like you're born all the way up at the top. You're mostly born at xenon-140, but there's some contribution coming into cesium-140, and some into barium-140, and some into lanthanum-140, and some into cerium-140. So if you look at cerium-140, it's got contributions from everything that came before it, plus its own contribution. This is what we call cumulative yields. And it's very complicated to work this stuff out. Another example, like you'll often hear me say, of it is an area of active research right now. In fact, one of my students, Eric Matthews, just published a paper on a code that takes decay information like this and puts it together with the fission product yield information to produce a prediction of what you will have at an arbitrary amount of time after a flash neutron radiation. So this is a code to enable nuclear forensics. It's called FIRE, for fission-induced electromagnetic response. It's now actually published. I can put it on eBooks. It's very proud of it. It's a really good paper. It's a really good paper. But this is really tough to do. It's hard to therefore look at this sort of multi-step beta decay fragment and figure out what sort of fission event would have caused it. There are too many other moving pieces that are in there. I like to describe fission decay as sort of, when you start trying to do fission product forensic analysis, it's when nuclear physics begins to look a little bit more like sociology, okay, which is a massively integral field of study. Okay, many, many different things influencing you. Often even have problems where you seem to lack reproducibility. Okay, it's very tricky. So now let's look around Promethium-142. Now I've zoomed in to this region. Any nucleus that you see here that's black is stable. Now remember that the way we feed these things is we start neutron rich, that's to the right, and we beta decay in along a diagonal. You'll notice that along the diagonals, you have the same mass number. And beta decay, generally speaking, the beta decay process itself does not change the total number of nucleons you have. It just swaps one for another. Okay, so you move along diagonals. It's like the bishop, if you would think of it from a chess analogy standpoint. And so what happens is, if we're down in this mass 140 region, you've got a lot of these beta decay paths coming across through these various short and then longer-lived radionuclides until they eventually arrive at something stable. And I'm going to call neodymium-144 with a half-life of 2.29 instead of 15 years. Yeah, that's stable. If you're a million times in the lifetime of the universe, it's that stable. Okay. But look at what happens as I move along the 142 axis. I get to cerium-142, and that's stable. Okay, it's 11.114% of naturally occurring cerium. Which means that the radioactive nucleus just behind it, Promethium-144, sorry, I shouldn't say it, and I now realize that I typed things wrong. It was praseodymium. Okay, PR, not PM. Praseodymium-142 cannot be fed by successive beta decays. They would all stop at cerium-142. So if you see any 142 praseodymium, where did it come from? Where did it come from? Fission. Did it come from beta decay? No, it didn't come from fission going through beta decay. It went straight from fission. It is shielded, and that's what we call it. It is a shielded nucleus. So the presence of this nucleus is a direct indicator of fission. If you know the yield to that thing, you know how much fission went on. Okay.
But not alpha. It can be alpha.
Can't be produced by alpha. No, it probably does have an alpha parent, but no, it wouldn't. It's closer to stability than the alpha parent. If it came from an alpha decay, it would have come from up there, from 146 per medium. Okay. And generally speaking, if you remember alpha decay really only happens with heavy nuclei, very heavy nuclei. Good question. Really, if you see this in debris from a test, you're looking at something that's much easier to interpret what the fission yield was. Okay. So the short answer was, so I wrote this very, now we have much more sophisticated ways now to look at fission. One of the things which I haven't gone into discuss is that as we raise the energy of the incident neutron, that bimodal distribution that we saw before, this thing, actually the valley begins to fill in, the peaks come down a little bit. We have lots of interesting ways of getting information about that are all open and unclassified, but they're beyond the technical view of this class, okay? But if you are a beginning weaponeer, those things might be a bit elusive. And a lot of those tricks that we developed because we had hundreds of tests to look at, underground tests where we could do soil corrections and things like that. We have a large database. And if instead you are a South Asian country, okay, a shielded nucleus looks very attractive. So, although I never got, it was funny, so I sent this email out, and there was a guy at Livermore who is an old event radiochemist. He's long since retired. In fact, I just recently learned that he passed away. That really flamed me and said, only a novice would consider using promethium to infer fission yields. And he's of course right. I mean, I was 2 years in. But then again, actually, India and Pakistan were novices at this game. Okay. And all of these other corrections that go in are, you need to have a fairly good body of experience to be able to have them. The great weapon we have in our arsenal, tool we have in our tool chest with respect to weaponry, nuclear weapons, is our experiential database, okay? We have a very large body of this, particularly for downhole test data. We have a lot of it, okay? So we know how to infer the diagnostics that we see coming out of this. And that really gives us a leg up. And of course, the Russians have a very large database as well. Okay. And this allows you to infer information from these sorts of radioactive product nuclei. And by the way, you look at this is actually not a bad half-life. You can see a little bit more clearly here. It's got two different decay paths. One goes to cerium-142, the other one to neodymium-142. Okay, and mostly it goes to the neodymium-142 path. It's a 19.12-hour half-life in both cases, which we liked 3 days. But if I was starting a new program, you better believe I'd look for this. Okay, this is something you have a shot with. You're not going to see a 20-minute half-life. It ain't going to happen. Okay, even an hour or 2 hours would be very hard. But this you could see. So I think it's worth noting that a country that wants to try to develop nuclear weapons and make them part of a strategic capability for them, it's really not very easy to do. There's a lot of sensationalism that suggests that, like, you know, any smart undergraduate from MIT, can build a nuclear weapon. Well, actually, they really can't. And if they could, it would be one pretty crummy one. Okay? You want to have a strategic capability with nuclear weapons, it actually requires rather a great deal of sophisticated technical expertise in a very wide area. Okay? And, you know, to be honest, one could make the whole argument that the whole purpose of stockpile stewardship is to make sure that we keep that technical acumen alive, that we don't lose it. People have referred to it sometimes as a jobs program for weapons scientists. Okay, I think there's some value to that. Certainly, I've personally partaken of that largesse over time. But really, it's true, because once you lose this technical expertise, you don't get it back. It's not very easy to do it, and there are very few people left who've actually done complete downhole shots and been able to interpret the radiochemical data that we have coming out of it. Like I said, at Livermore right now, I think the only person left who's an active scientist, I believe, is Ken Moody, who I'm still trying to get to come here and give a talk. Those of you who are taking, is anyone here taking Chem 146 semester? He's going to come and give a talk there. It's the vacuum lab that John Arnold teaches. Okay. Let me just ask you another physics question. Why not 140 instead? 140 for methane in this case. I grabbed this because I had this slide from before. Why would you look at that also along the mass 140 chain?
It's not shielded. It's
not shielded. Two things, it can be fed from cerium 140, you got it. And also, by the way, just to be clear, the lifetime is really too short. Okay? You really need 5.5 minutes, it's not going to work. Okay? So you have lots of these different fission fragments, but to try to interpret fission yield out of a fission fragment distribution is really quite tricky. Okay? So all of this, I realized it was worthwhile to take the time to talk about this particular example, not just because we've discussed India and Pakistan before. This is at the very birth of their nuclear capabilities, but also because it's at the core of stockpile stewardship. So stockpile stewardship radiochemistry 101, okay? This is still one of our best ways of getting information about the performance of our devices, was radiochemical data. But the thing you have to understand about our devices is that all of our modern stockpile devices employ boost. They have that DT gas, which means there's a huge surge of 14 MeV neutrons at one point. And that 14 MeV neutron comes from the DT reaction, which may have come from lithium-6 deuteride. Remember, there's two steps there. You break up the lithium-6 with a neutron, and then it becomes tritium, which then reacts with the deuterium. Okay, it's what we call dry fuel. The Castle Bravo test that I showed the picture of that used dry fuel. The large instantaneous flux of 14 MeV neutrons present in a thermonuclear test can cause what I call multifold N2N reactions to occur. What do I mean? Remember what our nuclear reaction notation. N, 2N means I put one neutron in and two neutrons come out. That neutron has to have enough energy so that it's not caught in the nuclear well and it actually knocks two other neutrons out. 14 MeV does that. Okay. Now, in general, nuclei are really small and it's hard to make even one reaction occur. But the density, the beam current of neutrons, 14 MeV neutrons in a weapon is huge. And so you do this, and then you do it again, and then you do it again and again. You just keep reacting. Because for a short period of time, the device is assembled at extremely high areal density, and lots of neutrons are being formed and moving through it. So if I start with a nucleus, which I've shown here, with a mass number A and a proton number of Z, okay, and I do an N2N, I make the A-1 nucleus. I can do another N2N and make the A-2 nucleus, and so on. And that's, you literally go right out quite far that way. Now, after a long period of time, and long in a nuclear weapon is a funny number, a millisecond. By the time you're at a millisecond, your anything vaguely neutron generating is over. The device is a fireball. We saw a picture of it before. I showed a picture of what this looked like at 1 millisecond. It was that round thing with the jets coming out that were the various guide wires holding the tower up. At that point, everything is over from a nuclear physics perspective. I mean, hell is about to happen, but the ball of flame is born, and all the energy and all the neutrons are done being produced. But the density actually is still quite high. So some fraction of those neutrons will start to scatter off of light elements. And there is rather a lot of light elements present in a nuclear weapon. It's not just metal. There's explosives, and explosives are light. Okay? And it will lower in energy. And when the energy becomes lower, if you remember our cross-section curves, when the energy gets lower, when we looked at cross-section as a function of energy, right? For a capture, what you saw was something like this. They all go up, okay? Eventually, neutron capture becomes dominant. We generally speaking refer to these neutrons as late time neutrons, meaning about a millisecond afterwards. Now, what do you think this would look like for an above ground shot as compared to a below ground shot? Which one do you think would have more of these neutrons? Why? You're right. Why would you say that?
You've got a bunch of material around that scattering neutrons back and forth.
That's correct. So when you're in a cavity, you're bouncing off of materials in the soil. Okay. Soil to first order is sort of silicon. Okay. Which when a neutron bounces off of something that's 28 times the mass, it basically turns around and comes back at you. Okay. Those, when we do our experiments up the hill, we call them room return neutrons. This is a new room that's born underground. Okay. And then they come back. And even though a large chunk of them escape, because the cross-section is much higher, the few neutrons that are left can capture over and over again. And so basically you come back to your A-2 and you can capture, make A-1 and capture again and make A. This is really a mess. You don't, of course, destroy everything you made in the first step, but you destroy some of it. And this really makes it quite difficult because the amount that gets born and the amount that gets destroyed, these cross-sections, by the way, although they capture cross-sections, are often referred to as destruction cross-sections, okay? That amount largely depends on cross-sections that we can't measure. These radioactive nuclei, like the praseodymium example that I gave before, 19 hours. You can't make a target of that. Okay, if I put a milligram of that target together, okay, if I was able to do a 19 hours of a milligram of that, and I had it right in the middle of this room, right now we would all get burned, okay, instantly because of the radioactive decay of that milligram of material, and we'd also all be dead very shortly, okay? And so you just literally can't measure these things. So we have to try to model the nuclear reaction rates to understand it so that we can take into account the production through N2N and the destruction through N gamma. So a lot of stewardship science was going back in and trying to understand what these cross-sections are, these things that we can't actually measure, okay? I personally did that for a couple of decades at Livermore. People are still doing this, okay? And what's interesting, an interesting side note about this, for the technical students in the class, do you know where else do lots of multi-order neutron capture reactions happen besides in weapons? Who says stars? Very good. Yes. I mean, reactors do as well, but nothing compared to a star. Over the course of its life, the star, through a couple of different mechanisms, makes basically all the heavy elements that we have around us, okay? I mean, colliding neutron stars make gold in my ring, okay? So those neutron capture reactions are of a great deal of interest to the basic science community, people in this subfield of astrophysics called nuclear astrophysics. And what I've always found very interesting is that if you walk the halls of building 111 and certain parts of 132 at Livermore, or the Metropolis building at Los Alamos, and you happen to know what names in literature, you see all these names of people who are nuclear astrophysicists. They're all there. A lot of them are students. They're students who went into this. During testing, this was really exciting for them. This was an opportunity to actually look at these neutron capture reactions, some of which you just couldn't ever imagine looking at from some other situation. I've known a couple of these folks. There's always been a very large interchange back and forth between those communities. Okay. So these reactions occur on all parts of the device. They occur on the fissionable or fissile materials, the plutonium or uranium, on the structural materials. Okay, as you can imagine, weapons have steel. Okay, anything else that you imagine structurally that a weapon could have, and a class of things which I call loaded detector elements. Okay, I'm going to give a lot of discussion about that. So we purposefully loaded certain elements into certain parts of the device so that we could look for these reaction products. And now the first thing that we loaded in every single weapon was either uranium or plutonium. Obviously, it wasn't going to be a weapon without uranium or plutonium. And I showed these pictures before, but I wanted to show them to you again. This is the plutonium. This is a piece of what we would call a plutonium reaction network. Okay, so what's loaded in the device is really overwhelmingly Pu-239. Okay, but if a high energy boost neutron hits Pu-239, then it can do end-to-end and make Pu-238. One of the things that we looked for a lot downhole was the production of Pu-238. We looked for the ratio of Pu-238 to Pu-239 in the debris. If you know the cross-section for that, you can infer the neutron fluence. And that was probably the measurement that most made my career, was measuring that cross-section for the first time. Now, again, it turns out particularly heavy nuclei, neutron capture is a really big deal. You do, because those cross-section curves all go way up, this is particularly a feature with heavy deformed nuclei like plutonium. You can get many multiple neutron captures. And as you capture the neutrons, you can see what happens. If I capture a neutron into a given nucleus, and that nucleus is even, like the capture on Pu-240 to 242, because I finished a pair of neutrons, I get a boost in energy, it fissions as well. Okay. Not so much when I capture on 242 to go to 243. You also, during so nuclear material in weapons, plutonium is not pure. Okay. There's always a certain amount of americium that's present, which was an ingrowth from the decay of plutonium-241. So therefore there's americium. And the americium that's in the weapon undergoes the same end-to-end and gamma reactions. Okay? And on out to curium. In uranium, we've often demonstrated it this way. Okay? In most weapons, the largest amount of uranium you have is actually U-238. That's the largest quantity of material that you have. And if you do a single end-to-end reaction, you make neptunium-237. Another one, you would make uranium-237. You make uranium-236. And then the captures can bring you back. Okay. So when you look at this, you realize, you don't see it. When you look at something like this, you realize that that there's a lot of information about the weapon present in the abundances of all of these residual nuclei, the products of these reactions, what we are often calling minor actinides. There's a lot of information in them. But most of these cross-sections are unknown. In fact, almost all of them are unknown. And collection efficiencies are very hard to calibrate. There's this quantity that radiochemists talk about called the bomb fraction. So you do a drill back into this molten slag pool at the bottom of a roughly spherical chamber where a nuclear weapon went off. And you go down into that, you recover some small fraction of the weapon. What fraction? It's not even reproducible, right? So it's very hard. So if I wanted to look, for example, at the production of plutonium-238 versus 239, and I dig a sample and I pull it out, I'd like to know what fraction of the plutonium-239 I recovered, okay? And that in turn depends on the chemical properties of plutonium-239. It turns out if you really want to recover material that was most intrinsic to the weapon during the time that it's going off, you want that material to be what we call refractory. You want it to have a very high melting point and vaporization point. So when the fireball is first coming apart and cooling down, it's the first stuff that freezes out. Okay, so that kind of the fact that things sort of separate out at different temperatures is called chemical fractionation, and that's another issue that folks need to understand. So unlike a lot, by the way, unlike a lot of my other talks where I was trying to give you a lot of in-depth, intuitive physical feel, I just have to wave my hands a lot here. And it's not because of classification issues. It's that every time I say something like chemical fractionation, I just throw that term out there. Like, you can get PhD after PhD studying this stuff, okay? It's really not a done field, okay? We do have a lot of data, which helps us a great deal. It's probably our single most valuable thing that we have is that data. In some ways, you could argue it's more valuable than the weapons themselves. Okay, so we did load other radiochemical detectors, and we just generally call this practice RADChem, into a weapon to provide insight. So I'm going to show you two of our favorites, yttrium and zirconium. They're extremely refractory. And it was that chemical fractionation property that most concerned the radiochemists. So when we went downhole and started doing shots underground, and now you have this other issue that these things are all present in the crust at some level, okay? They really want to know that they were looking at something that came from the weapon, okay? And that meant they were driven towards these extremely refractory elements like yttrium, zirconium, molybdenum, niobium. Okay, that's what they're all in this one general zone of the periodic table. So they did this, and from a nuclear physics perspective, I damned them all. These are nightmare nuclei. They're horrible. Yttrium is Z equal 39, which means that yttrium 89, the one stable yttrium, is N equal 50. It's a magic number. This means that nuclei in this mass region often have not just a ground state that lives a long time, but they have an excited state, which is like a higher order, higher octave note played on the string of the nucleus. These things are called isomers. They live for 15 seconds, or for 0.3 milliseconds, or for 14 milliseconds, or for 13.37 hours. So in a weapon, if you populate these things, so for example, I can make this 13.37 hour isomer at yttrium-87 by doing end-to-end on 89. Remember, 89 is the one stable one. And then another end-to-end at 87. But ending up at this isomer instead of the ground state. The minute I do that, that isomer is a target in the weapon. It could get hit again. All of these things do. So instead of having to measure just maybe 1, 2, 3 end-to-end reactions, I can do 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, it becomes horrible, and you have to get all of these. Okay, it's very, very tricky to try to do stuff like this. And in general, direct measurements on radioactive nuclei, as I said, are very difficult. So when you look here, we do have the end-to-end cross-sections off of 89 yttrium. That's the stable one. This is the thing you can measure in the lab. We did it. We did it in Los Alamos. We did it in Livermore itself. But in fact, I was even on a paper that was published on this. We measured these cross sections that populated all 3 states here in Yttrium 88. There was one truly heroic measurement by Renee Prestwood of the Yttrium 88 ground state end to end. It's a 108-day target. Okay, it was a truly, I call it heroic. This is a really hard measurement to do. Okay, I mean, there's actual physical danger involved with being around that target. It was done using a device called the rotating target neutron source, which after we were done playing with it at Livermore, it was actually sent here. And it lived for a whole while in the vault that now holds the HFMG on campus. And it dropped a whole bunch of tritium everywhere. You know, real nightmare that Carl had to clean up when he first came here. But bless his soul for doing that. Okay. Zirconium was used as well. Again, due to its refractory nature. And there's a neat little game that you can start to play, just to give you a sense of this. So you have a reaction network. Zirconium is a similar nightmare. You've got isomers and as well as ground states. And you can start to say, well, look, do I need to measure all of these cross sections? The answer usually is no. There's some that are more important than others. And it took us a little while to get to this, but my old postdoctoral advisor, Gene Henry, and I came up with a simple sensitivity study. We went through and did this. And yes, this is completely open and unclassified. It's where you should look in this particular case, because the spectrum that we used is not actually a real spectrum. It just has some interesting features to it. But we took that spectrum, I went through, this was a talk that I gave a few years ago, and I showed that in this particular case, if you went and you were looking, let's say here, at this ratio of 88 zirconium to 89 zirconium. 90 is the last stable ones. These are both radioactive, okay? You know if you see either of those two, you know that it was in the weapon, okay? It wasn't zirconium in the ground. If you look at that and you go in and you change the cross-section for zirconium 89 end to end to 88, if you do that by 50%, the abundance ratio there changes by 468%. So in other words, that's a money channel. You'd want to try and measure that or get at that no matter what. That one matters. A lot of the other ones just don't matter very much. Now, of course, this was a sensitivity study that we did for a particular arbitrary spectrum that we put together. It's not completely arbitrary. It had elements that we believe were realistic, but it was far enough removed from reality that we could do this. So these sorts of sensitivity studies are done to try to steer the program, to decide where you need to put your focus, the science-based stockpile stewardship program, what you need to actually measure. Because you got to do triage. When you look at that network, like the previous one that I showed, for Yttrium, if you really wanted me to go in and measure all of these things to say 10% because we've got 10 fingers and toes, okay? I mean, it'll be something that I'd be doing and my children would be doing and their children would be doing. Okay? I mean, it would be an endless task. So you really have to go in and make tough decisions. Sensitivity studies like this help. Okay. These studies are also helped if they are done in a physically realistic environment, but that's less important than you might think. Most of the nuclear reactions take place when the weapon is still quite small. Things have not disassembled. And often it's the nuclear physics properties that dictate our ability to infer data. So, are there any questions at this point? I want to just take a little bit of a break for a moment here. Gone through rather a lot. The radiochemistry stuff is very important. But for two completely different reasons. One, because we used it to understand how a weapon worked. Two, is because in the event that there is another nuclear event, either terrorist, if it's a full-out exchange, it won't be hard to figure out who did it, okay? But if a terrorist or a non-state actor were to come up with and use a nuclear weapon, you need to figure things out. And radiochemistry, again, is going to be one of your best pieces of information that you can get. It can tell you where the fuel came from. It can tell you the sophistication of the weapon. Yeah. And that's sort of the next part of what I was going to go through in this talk. So let's see where we are. I'm going to go into the next part. I'm a bit concerned about this. I don't want to. In the syllabus, what I originally had was that we were going to go into forensics and attribution next, which I do want to do. My concern, I've got the slides here, and so my concern is just that we won't be able to get through all of it. And then there's rather a long break with visiting lectures. Okay. I have to tell you, by the way, I looked through it again. Those two papers that I uploaded on B courses on forensics, one from Decker and the other one, his name is now escaping me, they're really good. Okay. I really recommend, and they're fun to read through. One of them is this really nice APS overview, American Physical Society overview of what's involved in forensics. So I do recommend that. But why don't I go ahead and give it a try and see how far we can go. Okay. Let's start here then. So what is nuclear forensics? This is the quote that was in these papers. Nuclear forensics is the analysis of intercepted illicit nuclear or radioactive material and any associated material to provide evidence for nuclear attribution. Okay. Nuclear forensic analysis includes the characterization of the material in correlation with its production history. And there's the link here, you can actually grab this. Again, all these links are live. Okay. This is the general field of nuclear forensics. So nuclear forensics doesn't necessarily mean that a weapon went off. Most of nuclear forensics relates, hopefully, continues to do so, with understanding where illicit material came from. Okay, this is one of the figures that's in that APS report. This is examples of what's called nuclear trafficking for all materials that could be associated with a nuclear weapon, and also specifically with those involving nuclear material, which generally speaking means plutonium and uranium, but it could include things as well like lithium-6, isotopic damage lithium-6, especially lithium-6 deuteride. This goes out to 2006, this plot that they have. What you see is a pretty constant rate of this. The number seems relatively low, but it's not. Because these trafficking incidents, you really don't need a lot of material to get to a point where you could do something if you are sophisticated, if you have the right technical capabilities. Now, attribution is another term that I was using. And attribution refers to the ability to identify the perpetrators of an act. For example, by typing an anthrax culture or performing radiochemical analysis of nuclear bomb debris. It is the key choice of responses such as retaliation or prosecution. And indeed, that word is true. You can have a legal case about the use of a nuclear weapon. And as you can imagine, the damages could be fairly significant. I think of the attribution program personally as being an incredibly valuable thing to have. Because, like I said, you can imagine the use of nuclear weapons is going in one of two ways. One is it's a state-to-state exchange, and there'll be no uncertainty about who did what, and that's called war. But the other one is that there is a non-state actor or somebody trying to remain stealthy who's gotten one of these weapons into a bad place and managed to detonate it. Okay. And then really, attribution is the statement that you can't hide. Okay. The one proven technology, sadly, that we have, or technique to ensure that we don't use nuclear weapons, is some sort of threat of retaliation. But the retaliation has to be correct. If the retaliation is against the wrong actor, you destroy the entire value of it. So you need to have a really robust attribution capability. And that's really tricky to do. And the interesting thing about a lot of the attribution program is a lot of the capabilities aren't as secret as you might think. You don't want to be secret about your ability to do attribution. There's actually projects that come out and they're very open about this. There's one called Project Discrete Oculus, which has sensors located all around cities. And PDO is there. These sensors will be run once, but they will give us information that we need. You want to have this information out there because you want the non-state actors to know that you can't hide. Now, the technical details of it, that's a different matter. We're going to keep that quiet. Any technical approach is subject to spoofing. One of the things that's rather comforting for me to see, especially in the time since 9/11, is that we've really worked through quite a few of the spoofing scenarios. We're pretty sophisticated at this point. And it's an effort that the US is leading, but it's not the US alone. Yes.
Sorry, what is spoofing?
Spoofing means I make the weapon look like it came from country X, okay? But actually the material came from country Y. I try to throw you off, okay? It's actually really hard to do that, and it's really, really hard to do it in such a way that you can deceive us. We're actually very sophisticated on this front. And again, we don't try to be secret about this, okay? Really, in a very short time after some sort of a domestic or international nuclear event, we will know a lot of information very quickly. And we'll use that information for what reason? Well, it's sort of in this order. Number one is prevention of additional detonations. It's one thing if the weapon was a one-off, okay? So for example, it's something that we know, like material that was definitely stolen at a particular point in time, or heaven forbid, actually a lost nuke, okay? Something like that. That's very different than if you see something right away and you say, okay, we know they got a hold of uranium X, and we know that there's enough for an additional 3 critical masses out there. Because once you've made one weapon, okay, what's to stop you from making more? And so the first question you have to answer is, will there be additional detonations? Second one is identification of and response to the entire chain of actors responsible for the detonation. So that's, you could say, well, it's pretty obvious. Whoever set up the bomb is responsible. But no, I mean, if North Korea sells special nuclear materials to another country, is North Korea culpable? I mean, I'm not a lawyer, but I would say they certainly share some of the blame, okay? And you need to have that sort of an answer. So you want to get enough information to be able to back that all out. And you want to be clear that we will have that information. Okay. Response and recovery efforts at the affected site in the United States, and lending appropriate assistance if abroad. Okay. This is one of the things that we definitely do want to do is help recovery. Particularly if the weapon is relatively inefficient, you're going to have a very large amount of nuclear material that's spread around. And that's something that you need to think about. Even a fizzle of a few hundred tons will spread a bunch of alpha over a local area. Again, you know, that's not going to kill a lot of people, but if you leave it out there, it's not good. You need to clean things up. Management of public and foreign government expectations and determination of the basis for further action. I'll leave that to you to imagine. What do you do? I don't know. You can play this out in many, many different ways because often there'll be multiple responsible parties, right? And so how do you figure that out? And what is the appropriate retaliation for that? What do we do? Hopefully this wouldn't be the case. What do we do if we find out that really, like clearly Russian pedigree fuel is found in some terrorist weapon? What do you do? I don't know. We had that interesting and difficult discussion about the Baltic nations in the last lecture. You know, these could be very, I don't think that would be a flavor that would necessarily happen, but I don't know. Okay, so there's a timeline. Yes, Matt.
And you might actually get to this now, but how long would it take to identify one of the actors in this for then a response to come? Because you obviously don't want to attack the wrong person.
That's right.
You don't want to wait, I don't know, 2 weeks after the fact either?
That's a good question. We practice and we drill over and over again. And we have test problems that we put together, and we run our community through them. Okay, the community of folks involved in the attribution program. So, and we need answers right away, and we need confidence limits right away. Now, there's sort of two answers to that question. There's the, what's actionable information? And then, like with that lead thing being with prevention of additional detonations. Then there's the legal standard. And I don't know, like that's a tougher one to go down. My wife's a lawyer. I've learned these terms, the difference between preponderance of evidence and beyond the reasonable doubt. My guess is this is more along the beyond the reasonable doubt. Before you nuke the country, you probably want to have no doubt, reasonable or perhaps even unreasonable. Okay. So some of this stuff you know pretty quickly. You know sizes of fireballs. You know approximate yield. You often know things like emplacement right away. When I say right away, I mean by the time the lab people are there, automated equipment has given them the information they need to stop. We know what happened. So, but do you know, what else do you need to know about? You need to know about the fuel source. You need to know about the weapon type. That takes longer. Yes.
So just a question about the pedigrees you were talking about a second ago. I mean, so other than changing the enrichment and stuff like that, how would we know that it was Russian fuel?
A lot of the minor actinides can be used for this reason. They tell us material has certain minor actinides present, which tells us about the reactor in which it was made, or the separation process that it underwent. There's a lot more in the written materials that I've dispersed, and I'm going to go through a couple of them here to try to answer that. But determining the fuel provenance is, we can do that actually fairly well. Okay. This whole idea, by the way, that all nuclear reactors are the same is ridiculous. It's not true. And their feedstock of fuel that goes into them is different. So now really what you want, and we have been working towards building, is a database.
So that was going to be my follow-on question was, so, I mean, like the United States, our nuclear program, and in particular our nuclear weapons programs are very, very closely guarded. So, I mean, maybe we have a database of all these things, but so, I mean, does every country have, I mean, is there a collaborative database, I guess, on nuclear weapons, for instance?
There are collaborative databases, absolutely. The IAEA does play a significant role in this, and we are partners with them. Now, that isn't to say that we give everything out, or that other countries would give everything out. But actually, when it comes to attribution, it's sort of in the interest of, at least of the major nuclear weapon states, that the information be good. Okay? What you don't want to have, I mean, is people going off half-cocked and making a bad decision. So in general, people do collaborate on this. Okay. Now, as you can imagine, Kim Jong-un has not been inviting people in to do fuel assays. Okay. So there could be some uncertainty, but there's less than you might think. Carolyn?
Oh, I just wanted to add the comprehensive test ban for organization is an international organization that has connection.
Yep. I mean, there is a lot of international collaboration and cooperation that goes on this front. Now, who has the most information? Well, we do. We did the most tests, okay? We did the most above ground. We did the most below ground. We did the most boosted. We did the most unboosted. We did the most multi-stage. We have the most information, okay? That puts us in a very unique position in this regard. And I think that this statement is true, that the US really has shouldered the majority of the burdens of this, willingly, because we also probably have the biggest target on our back of any country. So.
And that's one of the, in the advancement of our domestic nuclear forensics capability, we kind of operationalized it, and we make these partnerships with other countries to, if they had a nuke go off, that they can request our assistance to the State Department, and we'll go in and say, this is where we think it came from. If they, because not a lot of countries have an operational forensics capability today.
I mean, we definitely, our teams that do that sort of work. And this is, by the way, this is not just the teams that go in afterwards to try to figure things out. We have teams of people who go in before. Because of course the great hope is that you come across the weapon and you find it before it went off. Okay, and then we have a whole program called Render Safe that is all about exactly what it sounds like. And that's international. So we will send US citizens, mostly uniformed military, but not all. We will send them into harm's way to go in there to try to stop something from going off. And people who do this used to be called NEST. It's not anymore. But the people who do this are there for to make sure that that doesn't happen. But then we have specialized airplanes that can fly through clouds, and they're ready to do it at a moment's notice. Teams that will do debris recovery immediately. Okay. And again, then they're doing all of that to get the RADCAM information, which is really sort of the gold standard of what went on. It's that RADCAM. Okay. So some questions about the weapon we can answer right away. Okay, literally. Other things, the minute the radiochemists get a sample, they'll give you an answer. And then as you start to refine on, the picture gets better and better. Okay, and part of this is that we've generated, in addition to data about fuel, we've generated databases of potential outcomes. We're not going to have to be clever at that time. We're going to be able to go to one of these databases that we have and find a scenario that best reproduces our observables. And again, we're ready to do this immediately, anywhere in the world. So there's a timeline that has to go through afterwards, within hours. Was the event really a nuclear explosion? I know that sounds ridiculous, but you don't necessarily know that. There are fuel air weapons and stuff that can really be big. It can be an attempted nuclear explosion and the thing never went nuclear. You never established supercriticality. What was the yield? Okay. Within hours to days, was uranium or plutonium used, or both? Was the device simple or sophisticated? Were high-energy neutrons or tritium present, which would denote the presence of thermonuclear reactions, at least boost? Within several days of sample receipt by laboratories, you would know what was the isotopic composition of the fuel components. These are generalities that are here. They're much more specific information. What can be inferred about the problem in history? Does the debris match any from known weapons tests? And within approximately a few weeks of sample return, what was the most probable device designed? Does it match any existing designs? What other materials were in the device that may suggest a source? And you can get, as time goes on, and the reason why it takes time is why. Why does it take time? Some of these things, even if we do all the advanced planning as much as possible, it takes time. Why?
Chemistry takes time.
Chemistry takes time, that's true.
Example.
But actually, we've got that stuff pretty fast. Chemistry isn't slow down usually.
Radioactive decay.
Radioactive decay. Who said that? That's right. I mean, at the end of the day, I mean, I'm only going to you only ever recover small amounts of material, and you have to see the decay process go on. And a lot of that happens really early on, very quickly, and then it slows down dramatically. Remember that fission decay chain that I showed? You just got to wait and take data. Okay. When we did downhole shots, yes, Marissa.
So all of this is pointing to like the source of the weapon or who created the weapon, but when you're talking about non-state actors who likely couldn't have created it themselves and get it from somewhere else, like, is there anything? Are we just relying on intelligence to kind of figure out, the chain of, like, because you can imagine somebody having an interest in two superpowers destroying each other, so stealing a weapon and making it clear that it's from that state that actually being able to.
So that's a great question, because for me, it's totally hypothetical, so I can just answer it completely. But you shouldn't trust anything that I'm saying. It's not like it's informed. We probably, at the end of the day, if someone steals one of our weapons, do keep in mind, we still have the most weapons, okay? Somebody steals one of our weapons and uses it, okay, in any way whatsoever. What the attribution program will figure out is that it was one of our weapons. That's what it will do. Is there some way that I can tell who did it? Was it, one of the traditional media whipping boys, like some sort of a Middle Eastern terrorist organization, or was it a right-wing whack job? Sorry, that's not a term. It's a term of art, maybe. You don't know, right? I think that what you can find out with attribution isn't just what kind of weapon went off, but where was it? And then you can start figuring out, how did it get there? So if it was in some sort of very specialized, secure location, that tells you something. You're not going to have necessarily a sophisticated terrorist able to, like, let's say this thing goes off in some sort of in Sandia National Labs in, was it Kirtland Air Force Base? If it goes off in the middle of Kirtland, okay? Probably if you can show that, and you show that it's not just within Kirtland, but within a given part of Kirtland, you might be able to say, look, we know who gets in there, okay? You might have that answer right there. I think that part of this, it is a lot like, there's a reason why it's called forensics. It is reconstructing the crime scene and figuring out who had access and who had motive, obviously.
And we actually, in the operational programs, typically completely separate the forensics versus the attribution process. So the forensic is just the science, and then the attribution incorporates law enforcement and intelligence.
A lot of
all the
intelligence. That's what I
other-
was imagining. They needed all of that. Now it's mainly intelligence from forensics.
There is intelligence, but the science, just to be clear, the science isn't just what weapon went off. It's where did it go off? And yes, and you can figure out a lot of stuff about emplacement, really detailed stuff about emplacement. Okay, you can figure out whether it went off in the trunk of a car. Okay, even though that car is a former car. Okay, you can figure out things like that. There's a lot of information that the forensics process can give to the intelligence community, to the people who are trying to determine this.
Did you figure out if it had moved around a lot, like it had been in one country of origin and then had been in a very dramatically different country for a while?
I don't know. I mean, in my mind's eye, I'm imagining CSI with pollen. Yeah, that ain't gonna happen. The pollen's gone. Okay. I mean, there isn't magical powers here, but you can figure out a lot about where. Now, if at some point in that time that weapon was covered with with something to hide it, we might find indications of that thing. Okay. There is this picture that you have that the nuke goes off and it wipes out everything with it. Oh, no, not at all. Okay. In fact, if anything, material that's very proximate has very unique signatures that you can tell means that it was very proximate. Okay. So I think you take all of this information, you give it to the intelligence community, or they're part of it as well. There's some group of people who are trying to figure this out. Okay. My suspicion is that this would not, because we spend a lot of time and effort in doing this, it's going to be pretty hard to get out of this. Now, of course, what would then probably happen is you figured out, this was some AQ-Con design, okay, that had fuel from this location, and it probably came from this actor, and that actor is going to say, no, it wasn't me. So you still have that going on as well.
If we, for example, had a nuke stolen, would we admit it in the UN, or would it be a problem?
Personally, if you stole my nuke, I'd tell everyone about it.
Yeah.
I don't know. I mean, I think that, there are countries that have better and weaker command and control of their weapons. One thing is clear to me, at least, that the traditional scenario that most people think of is some terrorist after getting hold of a weapon. But you do have to remember that we have most of the weapons here. Okay, we have them. And I do like to point out that the first really big act of domestic terrorism that I'm aware of was Oklahoma City in modern history. And that was not a terrorist from abroad. It was domestic terrorists who did that. I think that everyone's thinking about these issues. and they have ways to catch for this. It's really hard, though, to steal an American nuke. Okay, it would be really hard. The whole military system is designed to make this really difficult. So I don't stay awake at night worrying about that. Okay, I think now my favorite thing to stay awake at night worrying about are some of the scenarios that Michael just spoke about. Okay, those are the ones that I'm staying awake at night worrying about, like what happens in a Baltic nation face-off.
Like if Pakistan, if they had a nuke stolen, would they admit it? Or just, pretend it didn't happen?
Or maybe it's not really stolen, right? I mean, they do occasionally pass things off to the Taliban, right? I mean, you don't know, it's possible. I would say, though, that if I were in command in Pakistan, I'd be very nervous about having one of my devices end up going off somewhere. Because I'm already born with the target on my back, okay? So I think that sort of stuff acts as its own deterrent. Part of this is that really we have not crossed the line since Nagasaki. And so now there's a special level of, the sense that you haven't crossed the line, you shouldn't cross the line, right? The first time that happens will be in a different world. So part of the scenario that worries me personally when I hear from Michael's description of like something going on in the Baltics, for example, is that if a nation uses one of these, then we've crossed the line, okay? And now it can start happening very often. So the great feature of attribution is that it works when everyone would be ashamed to have done this, okay? We're not ashamed when we send a Tomahawk missile to hit a country. We would be ashamed at some level, I think, if it had a nuke on it, but I don't know. This is far afield from the technical topics that I was needing to discuss, but let's see, we're at 3:21. So let me go through.
I should just add that there's been extensive effort by the United States to work with Pakistan on securing its nuclear facilities. And at least when I was in government, which is getting on years now, they were rebuffed. The US was rebuffed by the Pakistanis. Now, there may have been subsequent back channel, very compartmented, very classified activities. But Pakistan's been one of the major focal points for the United States because of there are terrorist groups there. There are terrorist groups that are supported by the government. There are terrorist groups not supported by the government. They have a large stockpile of weapons. It's a natural place for Al-Qaeda or ISIS or others to look to buy, steal, or to somehow clandestinely obtain one or more devices. So this has been a major issue for the United States. And in that nuclear security summit stuff that I mentioned, that Obama ran, throughout the 8 years of his presidency, there was no success with Pakistan collaborating.
And Pakistan is now, they are quite sophisticated at this point. So that definitely is a potential source of problems. But I don't want to dismiss any of the other ones. I mean, so let me go over something else here. I want to go over some of the, we'll start here. So what do you do with an interdicted sample? Okay. Remember that some of the material that you can get may not be nuclear. It may not be nuclear material, but it may be key constituent material for a nuclear weapon. So one of the first things that you do is you make this decision about what you're going to look at first. If it's a non-nuclear sample, you can do rather comprehensive forensic analysis. You can look at things like chain of custody, fingerprints. Now we can look at pollen, okay? Where dust, plant DNA, explosives. I'll go over some of these acronyms further on. A lot of this stuff relates to mass spectrometry, which is a technique that we use. It's kind of like those diagrams that we use for separation. We can tell what's in a sample, even if it isn't radioactive and decaying. Okay. If it's nuclear material, then we use radiochemical diagnostics. It's really the best thing. We can date the age of the fuel because some of those minor isotopes, minor actinides, have short lifetimes. So we can look at that and tell how old the fuel was. We can look at trace elements, not just actinides, but other trace elements that are put in. It's often part of the separation process that goes on. Look at stable isotopes. You can look at range, shape, and size. You can do this with atomic force microscopes, with scanning atomic electron microscopy of samples. X-ray diffraction, which tells you about crystalline structure, which could tell you something about how the material was cast or forged. Mass spectrometry. And you bring all of this together, and you have an interpretation analysis, and as it's called, case development. It's a legal sort of term, right? And then you're able to attribute and come up with a response. Okay. Let's see, we're close to the end here. This is just, I like, these are all tables that came out of that report. I put this one together with, from a separate portion, the acronym, the soup of language down here, of the various tools that we have, and when you would get to use them. So within 24 hours, a week, or a month, what would you do? Well, within 24 hours, you can estimate if it's radiological material, you look at the total activity. You look at dose rates from alpha, from gamma, from neutron. Some of the minor actinides actually have a small probability of spontaneously fissioning, and so you get a neutron output as well from that. Surface contamination. You look at the physical properties of the system. You can use a whole bunch of pretty sophisticated tools, like I said, scanning electron microscopy or transmission electron microscopy, energy dispersive X-ray spectrometry. All these things really can study surfaces and know about how samples were worked in some way, which tells you something about the capabilities of the place that this was done. Was it done in someone's garage, albeit a really sophisticated garage? Okay. Some of these things also, you have to keep in mind that the actor who would be involved in this might have been willing to die in the process of putting this thing together. You can see that in terms of the quality of the work that was done. People get shy as they start to get sick. So if you get to a little bit longer out, you can start doing various mass spectrometry, which tells you what elements are present, even if they're not radioactive. You can do this. So even after they've decayed to the stable thing that they're going to, you can do mass spectrometry. And there's one particular one that we like to use is inductively coupled plasma mass spectrometry. This is ICP stuff. Okay. Gas chromatography mass spectrometry. These are all different tricks. They're all related to making something charged, running through a magnetic field, and bending into a given angle, and you know by the angle what it was. Okay. Longer term, you still may have radiochemical signatures, especially if something did undergo an explosion. Okay, but you need to do different kinds of counting at that point. I thought this was kind of a neat table to put together. These are the different signatures that you can have for plutonium versus uranium, and what you would look for and what information would reveal. So, for example, for uranium, obviously, the ratio of naturally occurring uranium isotopes, 234, 238, and 235, can point to or exclude some uranium ore sources. Just looking at that, and that's something that you would do with mass spectrometry. Okay. For plutonium, when you look at isotope ratios, it tells you the type of plutonium production reactor that was used, the enrichment of the uranium that was put in as feedstock into the reactor, and it can even tell you about the neutron spectrum itself in the reactor. So give me some plutonium isotopics, and I can probably tell you exactly where this thing is, where that plutonium came from. That may not be where the weapon was made, but it's where the plutonium was made. So if you look at krypton and xenon isotopic abundances, I think this is kind of cool. It tells you about casting time. Why is that? What are krypton and xenon? They're noble gases. So when you melt metal, you release all of that stuff. And so then it starts to grow back in again afterwards. And that tells you the last time that this was done. So I really did get through virtually all of this. There's one slide in this one over here. I didn't go through it in great detail, but you can take a look at it at your own leisure. And I think that's it. We're at 2:30. Thank you.